Okay. Well, in the next 20 minutes, I'm going to elaborate on the topic of how stationary and mobile batteries can be used to support the German grid. I want to kick off my presentation by showing you the development of stationary battery storage systems within Germany. You can see an almost exponential increase until 2023, and since then a linear increase in energy capacity. Both industrial and large-scale storage systems here in dark blue and red increased by some extent, but the fact that we have doubled the amount of energy since 2023 is thanks to the large number of home storage systems that are installed in German households. Currently, we are counting over 2 million home storage systems, almost 20,000 industrial storages, and 371 large-scale storages. Although the industrial and large-scale storages increased quite a bit during the last years, it is still clear that the stationary battery storage market is dominated by the residential sector in Germany. But this could change very soon, as already in January 2020, 226 gigawatts of large-scale storage systems were applied for at the German transmission system operators. Honestly, we don't know how many of these projects are planned with serious interest, but even if only 10% of them are built in the end, this would triple the installed capacity in Germany. So this is definitely a hot topic at the moment. Why is this? Because batteries help us to better integrate the cheap but inherently unstable renewables into the grid. Batteries can help us with this in many ways. For example, they can operate behind the meter, where they can be used for own consumption optimization. So if you have a PV plant, a PV generation on site, batteries can help to optimize the own consumption. Also, if you have a power intensive manufacturing process, batteries can be used for peak load capping. Then they can, of course, be used for front of the meter applications as well. For example, for grid services, they can offer FCR, which stands for Frequency Containment Reserve, or AFRR, which stands for Automatic Frequency Restoration Reserve, only to name the two most famous ones. And of course, energy trading is also a possibility here. We are coming back to the behind the meter applications later, because I want to show you our latest research with our own large-scale battery storage system now, and this operates in front of the meter. Our institute has been researching large-scale battery storage systems since 2016. At that time, our system M5BAT with a capacity of 6.5 megawatt hours and 5 megawatt was one of the largest systems in Germany. There we looked at various markets and the implications of those markets to the different battery technologies that are installed in M5BAT. There we saw, for example, that for the FCR market, we achieve a pretty low round-trip efficiency of 78%. And this is due to the fact that in the FCR market, the batteries only work in partial loads. We also conducted a test that simulated intraday trading, and there we achieved a higher efficiency, but this is still not ideal. And then based on our experiences, we then developed a power distribution algorithm for multi-use operation. Multi-use means that we act on different markets there. And this algorithm then controls all existing battery technologies and inverters in such a way that we can achieve a much higher efficiency there. So in conclusion, installing and running a large-scale battery system is not as easy as building it on a green field. You need sophisticated solutions and software to run it smoothly. Of course, we also investigated the financial aspect with M5BAT. One driver of the large-scale BESS growth at the moment is the revenue potential there. We showed with M5BAT that we can achieve solid revenues in the FCR markets in the last years. We had one very exceptional year in 2022. But at the moment, it's still unclear how much revenue is feasible for the general battery system. There are many claims in the industry by traders that say, I can achieve this amount of money when you let me control your system. And there are even then, well, different claims there. So there is the lack of transparency. And we tackled this issue by introducing the battery revenue index a few months ago. And the target audience here are battery experts, traders, and a customer of traders. And as I already said, the focus lies here on transparency. So you can check out our results following this QR code. There you can also find the GitHub repository of the revenue index and download the provided data. Alongside transparency goes simplicity. So for this index, we only rely on simple calculations and do not use optimizations, so that it's easy to understand and reproducible. And regarding the reproducibility, there's currently also one paper in the pipeline. So now I'm explaining a little bit about the methodology of the index. On our website, you can configure your desired system of the battery. You can choose between different energy to power ratios, choosing between 1 hour, 2 hour, and 4 hour system. You can also select how many cycles the battery is allowed to perform per day. And you can also choose between different markets. There are, for example, FCR, AFR, intraday market, and the cross-market approach. And for the cross-market approach, the battery is divided virtually. First, a decision is made for the 4-hour slices of the day as to whether it is more attractive to participate in the FCR or AFR capacity markets. And then depending on the selected capacity market, the remaining power and energy of the storage facility is divided evenly between the AFR energy and intraday market. And then the revenues from these markets are calculated in the same way as the revenues from the individual markets. Here, I can show you some of these results for 1 cycle system, to the left for the 1 hour system, in the middle for the 2 hour system, and to the right for the 4 hour system. You can see that for each scenario, we calculated a set of days, and for each day, the cross-market approach outperforms all the other markets. And the most striking difference here is that the 4-hour system achieves much higher revenue than the scenarios with the lower E2P ratio here. So for the 1-hour system, we achieve 130,000 euros per megawatt per year, up to the 4-hour system of 435,000 euros per megawatt per year. Keep these values in mind. We will build on them in a few slides. Here I'm showing you again the growth of the stationary battery storage in Germany for the last years. Ironically, I'm showing you this because I want to talk about a different type of battery now, because I want to talk about the mobile batteries, so vehicles. Because if we compare these values here to the mobile batteries, so to the overall sum of the aggregated energy capacity in the German vehicles, then we can see that the capacity of vehicles is significantly higher than the capacity of the stationary storages. So if all these vehicles were connected to form a large storage facility, a so-called virtual power plant, it would be of great value, you can imagine, to the German economy to exploit this potential. But this has been largely untapped, mostly because of regulatory hurdles. But there are some companies like the Mobility House that wants to act as EV aggregators, so they aggregate the batteries of their customer vehicles alongside their own stationary batteries. And they capitalize on the fact that most of the time during the day, vehicles are parked in car parks, whether at work or at home. However, since the primary benefit of vehicle batteries is the mobility, not all of this capacity can be used at once. And the situation must be considered for different settings and charging behaviors, as you will see soon. So probably you're now wondering how much revenue can be generated by vehicle to grid in front of a meter. Unfortunately, this is still in development, so I cannot really give you an answer here. But what we can make is we can make assumptions altogether now and see where this leads us in terms of qualitative estimations. So here, let's assume that we are a company which is part of an aggregator fleet. Usually in the corporate setting, there's only slow charging, so we assume here 11 kilowatt per charging point. And in 2025, the average capacity of the sold cars in Germany is approximately 50 kilowatt hours. Then we also assume that we only want to use half of this capacity because we need some for mobility and some for safety margin. And this leads us to an E2P ratio of 25 kilowatt hours divided by 11, so almost an E2P ratio of 2. And then we take this value here of 237,000 euros per megawatt per year from the battery revenue index and multiply it with a few factors, for example, the daily availability, because considering charging behavior for fleets, we see in the first one here above that this fleet here is active on weekdays as well as on weekends. And this the second behavior here, this fleet is only active on weekdays and not on weekends, so only 5 of 7 days per week. Then we also can assume a discount factor, which accounts for the time period that the fleet is connected, because here in this example, the vehicles are connected from early evening to the morning, and in this scenario here, the fleet is connected from early morning over the midday till afternoon, which is much more beneficial for trading. So when we put in the values here, we get the results for one vehicle, then which is from approximately 800 euros per year per vehicle up to 900 euros per year per vehicle. And if we compare this with claims from the industry, here one from the mobility house, we see that we are ending up in the correct order of magnitude here. This does not seem to be an awful lot, but you have to consider that the primary use of the vehicle battery is the mobility, and that this is only the front of the meter revenue. You can make use of EVs by smart charging behind the meter as well, as I will explain now. This graph here shows the power curve of a sample fleet over one day. And currently the charging is mostly uncontrolled, and so there's no active load management. So charging power depends only on the technical limits of the charger and the charging infrastructure. And this causes sharp fluctuations and leads to significant load peaks and gradients, as you can see here. In the early mornings, there's basically no load, and in the early evening, there's a load peak of 250 kilowatts. And unfortunately, this is the peak that the station layout, that is significant for the station layout and grid connection point. Thus, this raises operation and installation cost. But there's good news, because the vehicles are connected during the whole night here in this example. And this is why the charging process can be shifted from the evening to the early morning here. There are still some other peaks left, as you can see. And to overcome this, you could install a buffer battery storage. And move the load to times where it is more convenient to you. For example, like here, or even like here for smaller peaks. And such a load profile is now manageable for most distribution grids. Once installed, the storage can be used flexibly and put to use for optimizing the load profile of the charging station. And as already said earlier, by joining an aggregator or pooling service, there can be made additional revenue by providing grid services here. To efficiently plan load capping or grid services, you need forecasting solutions. Forecasting for prices, for occupancy, for load. And one tool that helps with the forecasting of the charging points, at least, is a reservation tool where the user can schedule the charging time. And we developed this tool at our institute. Of course, we also optimized it for mobile applications. And not only does this tool give the user the peace of mind that the charging session is secured, but this information can be used by the energy management system as well for planning purposes. And knowing the flexibility instead of estimating it helps the energy management system a lot, because it makes it easier for marketing or for planning the load capping. So it helps in reducing the charging power. It can also help in another case where, for example, there are space constraints, because it helps to reduce the number of charging points required to fulfill all charging needs, because the occupancy for each charging point in itself is higher or can be higher. And this will, if you reduce the number of charging points, this will ultimately lead to a limited connected load then. We tested the impact of the reservation tool in a simulation for 6 different charging behaviors. 2 of them I showed you earlier, and on fleets with various sizes. And we find that the minimum number of charging points is reduced by 40% in this investigation, and this leads to a reduction in the peak power on average by 37%. So you see that predictability and prior knowledge of charging processes can help the energy management system substantially here. And with this, I end my presentation. And thanks for listening. If you want to know more about our research, then please visit our websites. To the left, M5BAT, in the middle, you get to interesting data about batteries and mobile batteries. And to the right, you can access the battery revenue index. Thanks you.
Thank you, Fabian. We will keep the questions until the end. And I already saw 2 questions online, so use the online chat if you want. Or for those in the room, they can also raise their voice then at the end. Now, our third and last speaker is Constanze Liepold from FCN, from my team. And she will present a study that we did lately on preferences in terms of willingness to accept direct load control. And the study was done for the German-speaking world, Germany, Austria, and the German-speaking part of Switzerland. Constanze, the floor is yours.
Okay, yeah, last time. I'm happy to get your attention. Imagine this scenario: you get home today. Yeah. Imagine this scenario: you get home today and you want to plug in your electric vehicle at your private charging station, but it doesn't charge. And why is that? That's because the local grid operator decided to reduce or cut off the power of the charging station due to grid stability reasons. This is a possible scenario that you could have if you participate in so-called direct load control. and this is what I want to talk about with you today. I looked into preferences in regards of direct load control and wanted to find out what is important to people like you, like me, what is important to people who own controllable appliances. Our roadmap today. For our roadmap today, of course, first of all, I'll explain you in a bit more detail what the motivation for our study is. After that, I'll present to you our research questions. We've got 2 of them, and I'll tell you how we investigated it. And after that, I will close with the results that we've got, including why batteries are the grid operator's best friends or should be the grid operator's best friends, and wallboxes are not. Yeah, you all know that our grids work at a frequency of 50 Hz, and whenever there is too much electricity consumed or too little electricity generated, the frequency starts to drop, which can cause, in the worst case scenario, the grid to shut down. To prevent that, we need a flexible demand, and this is where direct load control comes in. Through direct load control, the grid operator can send a signal to the appliances, a control signal, a pause signal, to shut down the power of the charging stations, and then that can help to stabilize the grid again. This tiny adjustment spread across thousands of households, of course, can also have a very big impact. Why is this important or gaining importance? Well, in the past, energy generation was dominated by fossil fuels, which are very stable and very predictable. And as you all know, this is not the case anymore now, because we want to shift our energy supply from fossil to renewable. And as you all know, you can't really predict when the sun's shining, when there is wind. And you also...
Yeah, not really. Sorry.
Oh, okay, sorry. Better?
Oh.
Good. Yeah, and historically, of course, that wasn't really the case. While direct load control has been very common in the industry sector, the research in this topic or in this field in regards of the private sector is very rare yet, because the appliances we formerly had in the private sector had a very, very low need for power, which changed because we started to electricize our mobility and also our heat generation at home. And of course, because of that, we've got a lot of demand within the private sector. And this also strikes why it is very important for us to investigate that. Yeah. And this is where our studies came into place, and we wanted to see what people would prefer in regards of tariff designs. We wanted to see what people prefer. But first of all, we asked how high is the acceptance for direct load control? Would people allow their appliances to be controlled if we didn't set any incentives? And the second question is, what preference do they have? Which tariff designs do you want? Which rules do you want? What kind of compensation would you need? There has been some research on this topic, especially in certain regions. We've got Mayotte, we've got the US, we've got Finland, but all of those studies have very small samples, and they also only cover single countries. And we use some of the ideas that former colleagues had, but we now have a larger sample, and we also covered all of the German-speaking DACH region. How did we do it? Prior to this study, we did a very small study with households who voluntarily participated in a direct load control program, and we asked them what they found important when it comes to tariff design. And based on that, we came up with this study idea. We identified a new socioeconomic status indicator. Socioeconomic status is normally measured within 3 dimensions, that's income, education, and occupation. But we found that it's also important to look into the asset ownership. Yeah, we came up with this new indicator, and we used it to classify socioeconomic status groups for each country. And for all of those groups, we conducted a CBC, that's a choice-based conjoint experiment and methodology we used. I will show or explain to you what we really did in the next slide. So I'll give you the examples. I think that's easier for you to imagine it then. And this experiment that we conducted allowed us to calculate so-called willingness to accept. That's the financial incentive that you can give people for them to allow, let's say, 1 more minute of control, for them to allow that the electric vehicle is controlled instead of the battery storage. I think you will see it when I come to the results. Yeah, and based on that, we were able to have results that we could compare across all status groups and across the countries, of course. Okay, so the scenario within the experiment was for the people to imagine that they owned so-called controllable appliances. That's a heat pump, a wall box, battery storage system, and air conditioning system. And then they were presented this let's say layout with 2 different alternatives. And as you can see, we have got different attributes that are important when it comes to direct load control. We've got the financial incentive that varied from 0 to 400 euros per year. We've got the frequency, so how often does your grid operator control your appliances? We've got the duration, how long does the grid operator control? The technology, of course, I mentioned those earlier, and also a control option, so an override option, whether you're allowed to say, no, I don't want my car to be controlled right now. Yeah, that's a quick overview of our socio-demographics of the sample we've got. This is representative in regards of region, age, and gender. The average age is 45. And as you can see, the sample is almost evenly spread across all of the countries. Okay, let's get to the results. Here you see our headline results. As I mentioned, we asked, would you allow it? Would you want your grid operator to control in case the grid needs it? And 70% of the people said yes. So people aren't fundamentally against it, but the details matter. And this is what I'm going to show you in detail now. Before I do that, I want to show to you how the results changed or didn't change prior and after the experiment. So we asked the people these questions before they really had a close idea how those tariffs could look. And then we asked them again after they answered the questions, the choice questions. And as you can see, yeah, the shares of people who would allow it are roughly the same, but there were shifts on an individual level. So some people who had previously agreed to direct load control wouldn't allow it anymore, and others changed the other way around. And this affected about 5 to 10% of the participants. So it shows that preferences are not fixed, and they can be influenced by seeing actual options. Yeah. Here you can see which of the attributes are most important to the people. Not surprisingly, financial compensation turned out to be most important. People care about what they get in return. Either the type of appliance that is controlled also matters a lot. Frequency and duration, so the timely aspects is a bit less important, but it still mattered, and the control option itself was least important of the 5 attributes that influenced acceptance. Okay. I can't show you a willingness to accept for the financial compensation because we need the financial compensation to calculate the willingness to accept. What I can say here is that all the results that we've got are statistically significant, but we can't directly compare the utilities of the attributes across the status groups because we use different models to calculate them. So it gets a bit more interesting when we look into the willingness to accept, for example, for the frequency. You can see a clear pattern here. The willingness to accept generally increases or stays constant as the socioeconomic status group increases. In other words, people who have a higher socioeconomic status are less sensitive to how often control events happen and therefore require less compensation. This pattern also holds across all countries. It's most pronounced in Austria and a bit less in Switzerland, and in Germany the willingness to accept is almost stable across all socioeconomic status groups. For duration, we see a very similar pattern. The differences across countries are less pronounced here. Across all countries, willingness to accept for longer control duration decreases as socioeconomic status increases. In other words, households with lower socioeconomic status require higher compensation to allow appliances to be controlled for longer periods. When it comes to the control option, we don't see clear trends here related to the socioeconomic status. Across all 3 countries, the willingness to accept doesn't really seem to be systematically or something here. And now this is what I teased before. Things get more interested when we look at the willingness to accept for different technologies. All the values you see here are relative to heat pumps, which we used as a baseline. And we calculated how much more a household would need to be paid in order to allow the control of the devices instead of the heat pump. The results are quite telling. Battery storage is widely accepted, often requiring little to no compensations. Wall boxes consistently show the highest willingness to accept. Across all countries and all socioeconomic groups, and air conditioners show mixed signals with no clear trends, neither in regards of the country nor in regards of the socioeconomic status groups. Okay. Of course, I can also the presentation was quite short, but I quickly want to summarize the findings we've got. The general acceptance is pretty high, and the socioeconomic status matters a lot. Richer and also higher educated groups are less sensitive, and the technology makes all the difference. Batteries are easier, wall boxes are harder. That means that we can't really have a one-size-fits-it-all solution, but we need the tariffs to be tailored to both the technologies and the socioeconomic status groups. Of course, we do have some minor or major limitations. This is a choice experiment and an online experiment. So while we do have we do know that the sample is representative when it comes to gender, and it can't really be representative when it comes to like society in general. That is a problem that we've got for all online experiments, really. And I'd say like this is the biggest lack, but also the biggest opportunity we've got. We don't have any real life experiences. So what people say could differ from what they actually do. And also we didn't model any comfort curves. So it might, or I'm pretty sure it does, make a difference whether the control happens when your electric vehicle is almost fully charged or whether it is not. Yeah, and we didn't really look into whether that is the case, which is what we want to do next. So we want to model those comfort curves. We want to maybe roll it out in the field experiments and see how people really react to direct load control, what they really find. And yeah, if you would want to collaborate on that, feel free to reach out. What I want to do before that is remind you or tell you that our partner chair at Constanze, you heard Karl's presentation earlier. He forgot to mention that we do some research on energy poverty. I want to mention that they are also doing some research on energy, on flexibility within the household sector. But they also do it like for industry. And I think if you really want to know what they are doing, you should talk with them. Jakob prepared those slides, but I'm sure that Aaron can also answer you the questions. Yeah, but what they do is look into the household sector, or they look into the industry sector and model different scenarios there. Okay, I think I'm done with the presentation also.
Yep. Thank you, Constanze. We have some online questions and I would like to take them first. Maybe Fabian can also join Constanze. The first question is by Alejandro Ristan. Do you have any data or any insights on the effect that each different marketing option has on the battery health?
Yes, in fact, we have. We operate M5 bats since the very beginning on the FCR market. And we see that the lithium-ion batteries that are installed, they are well, still in very good condition. So FCR and AFR are pretty harmless for the battery health. It is a little bit different for the energy trading because the energy throughput and thus the cycle depth and the amount of cycles is much higher there.
Okay, thank you.
We didn't test the intraday trading with M5 bot. We only did a few simulations and some tests, but not a long-term test.
Okay. Second question is also by Alejandro Tristan. On the vehicle-to-grid revenues potential, are you accounting for FCR or AFRR? Is it possible to pre-qualify such assets?
Yes, we considered it as we use the cross-market revenue value from the battery revenue index. And honestly, I'm not sure if it's already possible, but it will definitely be possible because otherwise the business case doesn't make sense.
Okay, thank you. The third question I have here is for Constanze. Can the operation of battery energy storage systems, when operated mostly based on economic incentives, introduce additional dynamic effects that negatively impact grid stability? I can repeat if you like.
I think I was able to follow you up until the last sentence because that seems counterintuitive.
So it's about the operation of battery storage systems when operated based on economic incentives. Do they introduce additional dynamic effects that negatively impact grid stability?
The only scenario that I could make up where this could be the case is when the power market or the electricity market sets price signal directly, which has nothing to do with the price signals that the grid operator could set. And we've got a dynamic pricing that, that sets the incentive to consume a lot of energy at the moment where you've got a lot of generation within the grid. And if then multiple battery storage systems or multiple wall boxes, also multiple heat pumps, react to those price systems that come from within the electricity market, that could cause local insecurities for the local grid, because then the consumption would be very high within certain areas where you've got a lot of heat pumps. And then this would work against the mechanism of direct load control, because if we had dynamic pricing within the direct load control or within the grid freeze, that would work against this dynamic pricing mechanism when it comes from the electricity grid.
Okay, yeah. Dear Kuwe. Sure.
Thank you. The main problem we see is especially because we have this one price zone in Germany. Yeah? So if we have lots of wind in the north, the price drops towards zero. But in the south, not necessarily is power. So the batteries start to charge. The energy-intensive industry starts to ramp up their consumption, and the power plants ramping down. Yeah.
Right.
So this is a general problem, not a problem about batteries alone, but these batteries obviously would do something very bad to the southern German grid in this point of time. Could be for sure the other way around as well. Yeah. So, but we're coming more and more in really trouble, I would say, with these pure price signal as we keep the one price zone in Germany. Yeah. So I think this has to be addressed much more. I know politics is not really willing to go into this direction, but we have to find ways, yeah, because it absolutely makes no sense. Generates a lot of cost, because then for sure the grid operators will ramp up their additional power plants at a very high price.
Yeah, a large country with only one price zone.
Yeah.
And
Yeah, that's what I meant. Thank you for putting it into the right words.
You put another point, the grid.
Yeah.
Is another thing. Yeah, so this is just markets. Yeah, it was totally additional to the point.
okay, not just that's a bit funny, because the question that I addressed to Constanze apparently is referring to the first one. The first presentation, second overall in block, but that is Fabian's presentation. So Constanze gave an answer to a question that was supposed to be addressed to Fabian. It was not clear in the chat.
I think
we covered it quite well together. All right, I have another one by Dirk Müller.
I think next year the first automotive companies will offer tariffs for vehicle-to-grid application, and then they have only a lithium-based battery technology. So, but actually, when I would use it every day with my car, then I have a lot of small cycles, because, as you said, it will be only part load of the battery, because I still have to drive to work next time. So how it's about aging when I have the small cycles, because I have a high number of cycles, but actually all of them are very small.
Yes, a colleague of mine investigated this, I think 2 or 3 years ago, and he found out that offering these services will lower the average SOC of the battery, which is beneficial for the calendaric aging. So this is well, a plus point for a battery aging. Of course, you're doing more cycles. This is negative, but in the end, he found out that these two effects will cancel each other out. Yeah.
We're modeling. Look at your lead acid starter battery in the car. If you do a full cycle, you can do 20 to 50, 20 to 50. The starting is just 1% of the capacity, and this is, you can do 10,000, 50,000. This is exactly what you, this is what we model this with the.
Okay, thanks for that comment. I don't see any online question anymore. There's one more hand, Aaron.
Thank you. A question to the first or second presentation. When modeling against FCR or AFRR, do you see these potentials, these monetary potentials also for the future? Because with more batteries coming into the market, first we have cannibalization effects. And the second point would be with the presentations that we had in the earlier sessions with more digitalization, more data exchanges. I suppose that in the future we may not have these huge differences between what has been traded and what has been physically consumed. So maybe the overall need for control power goes down. What do you think?
For the last question, we already see that there's a lot higher share of virtual trades than physical trades right now. Yeah, if we can rid of the control mechanisms, we will see in the future. And sorry, can you repeat the first part? Yes, there will be some cannibalization effects, but at the moment we need these markets, so there always should be a business case to pursue these grid services. Yeah, you can expect to still make money with it.
Okay, thanks. I think time is up. Before closing the session, I would like to thank all three speakers. The first one is no longer with us, but Fabian and Constanze, thank you. I think it has also become clear in Constanze's presentation what we as economists mean by utilities, right? That is related to utility theory, the theory of the private household rather than a company. And the last hint is there is a new book publication out there, a little advertisement, by Edward Elgar. It's a new research handbook on energy management with 21 chapters. I'm one of the two editors and a contributor to one of the chapters. So if you're interested, the flyers are somewhere around. That's a new and I think useful book for many of you. With that, I close the last session and hand over to the conference chair, Dirk, for the final announcements.
So actually there's no big final announcement, but thank to all the speakers we had today. I think was a very interesting mixture, seeing perspectives of different institutes on the same topics. And also I think the 4 topics we are addressed are very different, but all contribute to the energy transition and all bring own tasks for the future. So I'm very grateful that I also can work for the next years in the field of the energy transition, because it will be as much fun as it has been in the last years. And I think we can answer many of the interesting upcoming questions with our work. And also thanks again for all external speakers joining us today. Thank you.
Thank you.